Question 11 says, two small equally charged spheres, each of mass m, are suspended from the same point by strings of length L. The distance between the spheres is x being very small compared to L. If the approach velocity varies as v is equal to a by root x, where a is a constant, then the rate of charge decay, leak-off, of each sphere is, and we have been given these four options. Well, the way to solve this question is, we just draw the situation schematically. These are the two spheres. Distance between them is x. This is the point of suspension. So the electrostatic force, let's consider the left sphere now. The electrostatic force will be 1 by 4 pi epsilon naught, and if they have charge q each, so it's q square upon x square. Then of course there is weight mg, and there is tension T in the string. This angle is theta. This angle is theta 2. And we can see that T cos theta equals mg. Let's consider the equilibrium, because we can consider that the acceleration is small, so we can still consider the situation to be in equilibrium. T cos theta is mg, and T sin theta equals q square by 4 pi epsilon naught x square, and dividing the second equation by the first will give us tan theta equals q square divided by 4 pi epsilon naught x square into mg. And x being very small, we can replace tan theta as x by 2 into L, and so that is equal to q square divided by 4 pi epsilon naught mg into x square. And let's further simplify this. We are interested in finding minus dq by dt. So the expression for q square then is 2 pi epsilon naught mg xq divided by 2l, by rather L, because this 2 is already taken care of. And if I differentiate both sides, I get 2q dq by dt equals 2 pi epsilon naught mg by L into 3x square dx by dt. Again, I remove these two, and we have expression for dq by dt. Actually, strictly speaking, we are interested in finding minus dq by dt. So I put a minus sign here. The rate of leakage of charge will be minus dq by dt, and there's a minus sign here. Minus dx by dt will be the approach velocity, and so we get minus dq by dt equals 3 pi epsilon naught mg divided by L x square into minus dx by dt, that can be replaced as a divided by root x. And of course there is q2 here. So for q we can again go back to this expression, and if I use q from there, I get q will be equal to under root of 2 pi epsilon naught mg xq by L. And if I substitute this value of q here and simplify further, we will find that minus dq by dt term will be equal to 3 by 2a under root 2 pi epsilon naught mg by L, which means option 4 is correct for this question. Let's go to question 12 now. Question 12 says, a ray is incident at an angle of 53 degree on a prism and emerges at an angle of 37 degree as shown in figure. If the angle of incidence is made 50 degree, then angle of emergence can be, and these are the four options, and we have to select the correct one, of course. Well, to solve this question, let's simply look at the graph of angle of deviation versus angle of incidence, and that graph looks something like this. Here is angle of deviation delta, and here is angle of incidence I and E. Of course, the angle of incidence and the angle of emergence can be interchanged, right? They form a conjugate pair, and their values can be interchanged. We know that. So this graph looks something like this. not exactly symmetrical, but it's something like this. This is what we call the angle of minimum deviation, and here values of I and E are exactly equal. Now in our case, angle of incidence is 53 degree and emergence is 37 degree. So we can say somewhere here, we are of course not at the extreme situation. So somewhere here, and that's because for the extreme situation, one of the two angles will be 90 degree. So let's say we are here and this corresponds to angle of incidence 53 degree. So if angle of incidence is 53 degree, the corresponding value of angle of emergence will be 37 degree. This is the situation now. And what is being done? Well, the angle of incidence is reduced to 50 degree. That means clearly from this side we are coming somewhere here. And the two things are happening. One, that the angle of deviation is being reduced. Now what is the expression for angle of deviation initially? Say, let's call it delta 1, the initial angle of deviation. It was I plus E, and I plus E initially was 90 degree. 90 degree minus the angle of prism. And in the second case, delta 2 will be equal to 50 degree, because that's the angle of incidence, plus let's say E2 minus A. But there are two things to be observed here, that delta 2 will clearly be less than delta 1, which actually means that 50 degree plus E2 is less than 90 degree. This condition has to be satisfied. And further, that the angle E2 will be greater than 37 degree. We can see that corresponding to this angle E2 will be clearly greater than 37 degree. Well, the only option that satisfies both the conditions is option 2, where angle E is taken as 38 degree. Other angles will not satisfy both the conditions simultaneously. So option 2 is correct for question 12. Let's go to the next question now. Question 13 says a satellite is revolving around Earth in a circular orbit of height h equal to 2r from Earth's surface. If the satellite is stopped suddenly and allowed to fall freely, then the speed with which it hits the surface of the Earth is, well, clearly r here stands for the radius of Earth, and to find the speed with which it hits the surface of Earth, we will simply conserve energy. Okay, so when the satellite is stopped at height h equal to 2r from Earth's surface, it has only gravitational potential energy, and that gravitational potential energy, let's call it Ui, is equal to minus G capital M, which is mass of Earth, into mass of satellite, divided by distance from the center of Earth, that will be equal to R plus H, that means 3R. And initial kinetic energy is 0. When it is about to hit the Earth, its potential energy is simply minus G capital M small m by R. So the loss in potential energy is equal to gain in kinetic energy, and which gives us the expression half mv square is equal to Ui minus Uf, which gives us G capital M small m by R into 1 minus 1 by 3, or simply 2G capital M small m by 3R. We can strike off small m, and V turns out to be then under root 4gm by 3r. So this is equal to then 4 by 3 gr, or simply 2 root gr by 3. If we look at the options, this is matching with option 3. So option 3 is correct for question 13. Let's go to the next question now. Question 14 says two tanks of cross-sectional area A and 2A are connected together at their bottoms by a pipe of small cross-sectional area small a and a tap as shown in figure. Initially the tap is closed and tank with cross-sectional area A is filled with water up to height h. Now the tap is open at t equal to 0 and water flows from one tank to the other. The time taken to equalize the water level in two tanks for the first time is, okay, so we have these four expressions. This is the diagram given. This tank, obviously this appears to have smaller cross-sectional area, so this is let's say has cross-sectional area A, it is already filled, and the other one has cross-sectional area 2A, and this tap is open at t equal to 0. The cross-sectional area here is small a. So at any time, the speed of efflux V can be given as root 2gh, okay, where h is the difference in the levels of the two sides. So if the height of liquid on the left side is h1 and the height of liquid on the right side is h2, then h is simply h1 minus h2. This is the speed of efflux. We know, we get it from Bernoulli's equation, and the expression here will be this in this particular situation. Further, the rate of volume flow will be the cross-sectional area small a multiplied by root 2gh, and that means cross-sectional area on left side is capital A minus a dh1 by dt. So minus dh1 by dt is actually the rate of decrease of the level of liquid in the left part, and that is equal to 2a into dh2 by dt, and it's also equal to small a into root 2gh. Well, so let's solve these two equations first to get a relation between small h1 and small h2. So to do that, I simply cancel dt on both sides and integrate. So I get on the left hand side minus h1, and the initial value of h1 was capital H. Let's say final value at some point is h1, and on the right hand side then we will get 2 times h2, and the limits of h2 will be 0. Its initial value is 0, and let's say the value final is h2. So this means we have h minus h1 on the left hand side equals to h2. This equation relates h1, h2 and capital H, and now further let's use this equation, and we get minus dh1 by under root h equals small a by capital A, and then it is under root 2g dt. Okay, from these two expressions, this is the equation we get, and to make it possible to integrate, we write h, which is h1 minus h2. So h2 can be written as capital H minus small h1 by 2, and this gives us then 3h1 minus capital H by 2. That's the value of h. We replace it and integrate with proper limits. When the levels become equal, then h1 and h2 are of course equal, and using the conditions that we have already got, we find that the time we get is solving and of course replacing h by this expression here and carrying out the integration. The value of h1 when the levels become equal, we have h1 plus 2h1 is equal to h, or h1 will be then equal to h by 3. So from h it becomes h by 3. That's the proper limit for the integration, and then solving it we find that value of t turns out to be equal to 3a by 2 small a under root 2h by g, which is matching with option 4. So option 4 is correct for question 14. Let's go to the next question now. Question 15 says, in the arrangement shown, the ring can slide over the smooth rod vertically. The time period of small oscillations is, and the 4 options are given here, and this is the arrangement that's been shown. Well, obviously the question is from the topic oscillations, and to find the time period, basically our strategy will be to just displace the ring from its mean position by a small distance x, and then look at the restoring force. So if we displace the ring from its equilibrium position by distance x, which is small, then if you consider that there is a small displacement x here, this length, if I say x, then the elongation of each spring will be x cos 45 degree, that means x by root 2. That is for the right spring as well as for the left spring. So that means the restoring force on the ring will be in this direction kx by root 2 and also in this direction kx by root 2. X being very small, this angle will still be 90 degree because these two angles are 45 degree. And so the restoring force is the resultant of these two forces, and the magnitude of the restoring force is then, because they are at 90 degree angle, so the resultant will be kx only. So it is kx. And so our equation becomes m d2x by dt square mass into acceleration of the ring is minus kx, minus sign coming because the direction of the restoring force is opposite to the direction of x, and this gives us d2x by dt square is equal to minus k by mx, which means the angular frequency omega is under root k by m and the time period t is 2 pi by omega or 2 pi root m by k. If we look at the options, it's matching with option 1. So option 1 is correct. Let's go to the next question now.